of exactly the same structure, and this dark area is the strontium titanate. And that shows pretty much the same thing what happens. And here is a picture from the electron microscopy data, which shows that indeed there is a curl of the polarization. That's very important because under normal circumstances, if this were classical, this would simply form up-down domains. And there is no curling except at the domain wall. The curl of the polarization goes to zero everywhere except at the domain wall. But in this case, the curl is non-zero everywhere in the material. So the material is continuously rotating the dipoles. And if you're a ferroelectrics person, you say, that's very interesting, because all the textbooks told you that ferroelectrics are the extreme case of large anisotropy, and therefore they should not be able to do this. You cannot deviate the dipole away from a particular axis, in this case, a tetragonal axis. But indeed, it happens. And the reason it does that is because we impose some very intense boundary conditions. If you write down the Hamiltonian for the system, we won't go into the details of each one of those terms, but there are four terms: the bulk Landau energy, the gradient energy, the elastic energy, and the electrostatic energy. And it turns out these two guys are approximately same order of magnitude. So if electrostatics simply controlled this, if I had my lead titanate polarized out of plane, it says, I don't want to do that. I would be much better off if I put my polarization in plane. Unfortunately, or fortunately, in the case of ferroelectrics, the dipoles are very strongly coupled to the lattice. So when the dipole goes in plane, the lattice also distorts in plane by a few percent. And if that happens, epitaxy says, no, you can't do that. So the elastic energy takes over. So it's this confusion, this kind of contraindication, or the fight between these two energy terms makes it go into compromise state where the dipoles are actually rotating. Now, if you look at the structure by phase field calculations, you can see exactly the same thing happening in calculations. This is one of those vortex-like structures rotating clockwise. And if you look at it from top, it looks like a whole bunch of tubes. The diameter of this tube is 5 to 6 nanometers. So it's perfectly in the nanometer regime. And it turns out there's a whole bunch of beautiful physics associated with this. The first thing that you can see is if you look at these vortices from the top, it looks very much like they have a sense of alignment. And that's because the substrate that we use is an orthorhombic structure, dysprosium scandate, and so it has a preferential direction. So that's the first thing I want you to notice, that there is all these vortices are going top left, bottom right. The other thing that you can see are these boundaries. They look like antiphase boundaries, and they are antiphase boundaries, where the vortices are shifting by half a wavelength with respect to each other. The other thing that I'm going to show you is something which I'm very fascinated about, and we are deep into it. We haven't figured this out yet. If I look at a very local region, you can see that that's the antiphase boundary. But what you will also see is a whole array of dislocations. These are not dislocations in the fundamental lattice, which is a 4 angstrom unit cell. These are dislocations in the vortex lattice. Okay. Then if you have done, for those of you who are superconducting people, I'm sure you've seen Kostelis and Paulus's beautiful work, right? How do these phase transitions happen? Professor Mermin's classic Reviews of Modern Physics article on 2D phase magnetic transitions. So we've been sitting here saying, maybe we can understand phase transitions in these systems because of the existence of these kinds of dislocations. And so we are pursuing it with a lot of intensity, doing dielectric measurements, temperature-dependent scattering measurements, microscopy, to see if this system, this 2D kind of a structure, also behaves very much like a KT system. And nobody's ever shown that in these kinds of systems. It's been shown in superconductors, in other systems, but not in this dielectric or ferroelectric systems. Now, looking at another exotic picture, an exotic manifestation, Saif Salah. It's a pleasure to work with the architect of each other. But if you write down the free energy landscape for one of these ferroelectrics, below that transition temperature, it'll look like this double well. And you've seen it in textbooks, very classical. Now, typically people will pay attention only to this value and this value. That's the up and down polarization or left-right polarization. Nobody will think about this point in that space because that's the unstable part. Why? Because the curvature of the free energy landscape is negative, which means that the permittivity of the system, which is related to the curvature, is negative. And the reason it's unstable is it'll just roll down this energy well and get located here. Okay, and you can also look at the electric field, and that's basically telling you the same, that the capacitance or the permittivity is negative. Now, we wrote a paper, Saif and I, a while ago, maybe in 2012, we wrote a paper saying that in lead titanate thin films, when you switch the polarization state, you can access negative permittivity in temporal domain during the switching process. Now, in equilibrium, you're not supposed to be able to access this point because it's unstable. On the other hand, that equilibrium is meant for the entire material. That's the equilibrium state, ground state of the system. It doesn't tell you about the local or spatially resolved energy landscape. And so for the last 3 years or so, we've been working with David Mueller, a fantastic microscopist, electron microscopist, where we can take an angstrom electron beam and you can shine it on these vortices. One is the counterclockwise and the clockwise vortices. And it turns out that this angstrom beam will start to rotate. So you can change the angular momentum for the electron. And that is actually mapped out here as a function of spatial location. It turns out that angular momentum changes essentially by h bar by 2. We don't know whether that is something like a quantum number or that it just happens to be. But very, very systematically for the right rotating and the left rotating, the angular momentum will change at the scale of h bar by 2. Now you can map all of this with state-of-the-art microscopes. Then we said, okay, can we go one step further? Can we go in and measure the torque? Of course, we can measure the torque. That's essentially what the angular momentum plot is showing you. So you can quantify the torque. You can also do holographic kind of measurements to get the potential, the local potential. And you can convolute the two of them to get the potential energy. I will not take you through the math because it's a little bit complicated, but this paper, Ajay Yadav, who was a fantastic student from IIT Kanpur, he published like 3 or 4 Nature papers with us. Now he's sitting at Applied Material. I said, dude, what are you doing there? You should be doing science. So if you look at this, you can see that the energy landscape is looking very much like what you would see. Oh. The landscape looks very much like this, that you can actually see minima as well as the maxima. That maxima is shown here and here. I guess this is what I was being. That maxima is right here and here, and in between them, you can see the minima. So in principle, you can, not in principle, in reality, you can map out with essentially unit cell precision the energy landscape of the system. And it's telling you that within these vortices, right at the core of the vortex, you have the maximum in the energy of the system, which kind of makes sense because that's really where the domain wall in a classical system exists. Okay? So you can now start to say, what are the properties of these kinds of arrays of vortices? Now that you know that there's negative, that it is sitting at the peak and there's negative permittivity, can you measure it? And in a few minutes, I'm going to show you that data. So then we went forward and we plotted all of the data together, and you can indeed plot out the full energy landscape, and it looks like so. It looks like so. And therefore, you could see that right at the core of the vortex, there is a peak in the total energy, normalized energy. Yeah. And so that tells you that indeed you can have regions where the curvature or the permittivity of the system is negative. It is not the entire material, but it's only spatially confined. Okay, and then phase field calculations indeed did show that you can have this. Now, Saif was involved very heavily into negative capacitance because he thinks it's a pathway to reduce the so-called Boltzmann tyranny, the 60 millivolts per decade of IDVG curve by using negative capacitance. And these kinds of skyrmions and vortices are very big for that. Let's now talk about something even more exotic. And this is, I'm very fascinated by this because it's such a fundamental aspect of nature. This has to do about chirality. And you all know, many of you deal with chiral systems. A magnetic system by definition is chiral. But, a good example would be amino acids or if you look at amino acids or sugars, for example, they're all handed. And nobody still knows why the human system only uses L amino acids or D sugars. We cannot assimilate L-glucose, for example. So chirality or handedness, it's a geometrical property, spatial layout of the objects, where you cannot superimpose it on the mirror image. Okay. Typically, you do optical measurements, D-glucose, dextro, L-glucose, levo, and all the chemistry language that we've learned. And typically, you would do it with optical measurements, circular dichromosome. Yeah. And here's an example of skyrmions, is an example of a screw, for example, which is also a handed object. Okay, now it turns out, how does one go about measuring it for these things? I'm going to take you very quickly through X-ray absorption spectroscopy. We have the biggest expert, Didi is there in the audience, so I should not be speaking, but we do use a lot of X-ray absorption spectroscopy. In this case, looking at the 3D orbitals in, let's say, for example, titanium. Those are the EG and the T2G orbitals. And so these transitions basically go from the filled 2p to the empty 3D orbitals of titanium plus 4. And so you can have the spin orbit splitting, which gives you the 2p 3/2 and the 2p 1/2, or you can have the crystal field splitting, the EG to T2G. And so that leads to spectra, absorption spectra like this, where you have the L3 and the L2 corresponding to these transitions. And then the question is, what can I do with this? You can probe the local environment, oxidation state, the site geometry. Is it still tetragonal, cubic? All of those things can be studied. You can use linear and circularly polarized X-rays to study them. You can look at orbital physics, ferroelectricity, magnetism, and you can also look at chirality. Perhaps one of the biggest experts on this next technique is in Oxford at the Diamond Lab. Steve Lovesey is just an amazingly insightful guy. So the technique that we have been using to probe chirality in this vortex lattices is a combination of diffraction with spectroscopy. And this is called resonant soft X-ray diffraction. Didi, of course, knows a lot about this, so I should not be speaking about this. So imagine that the simple version is, imagine that I had a vortex which had a certain periodicity. In our case, the vortex periodicity is about 6 nanometers, or the vortex to vortex spacing is about 12 nanometers. If I go to that value of Q, sit here, and then I do absorption spectroscopy, I can start to look at what the periodicity of the vortex lattice will do. And if you look at that, that was a kind of a staggering piece of data that we got. It took us about 2 years to figure out what it is. What you see here is basically the diffraction data that I showed you in the previous slide, except it is in the form of a spectrum. That diffraction data is for circularly polarized light, positive and negative. And in ideal terms, unless you had a ferromagnet for a material like a ferroelectric, there should have been no difference between this red and the blue spectrum, because there is no magnetism. But it turns out that if you have a chiral material, if you have natural circular dichromosome, for example, then you could have circular dichromosome even though there is no magnetism. And indeed, this was the first piece of data which said, hey, these things are chiral. They have a handedness to them. And also the fact that the plus Q and minus Q are antisymmetric is a good indication that it is indeed a chiral object. And the chirality can be described like so at the bottom. This is from ab initio, second principles calculations, which shows that if I have a vortex rotating clockwise with an axial component of the polarization, and another one doing counterclockwise with the axial in the opposite direction, both these guys are basically right-handed. And conversely, the other form of it is left-handed. And it turns out that this was an incomplete picture 2 years ago. We now know that you can have these vortices move up and down. There are so many ways to create chirality in the systems. But when you look at macroscopic samples, indeed, we found regions with positive circular dichroism and with negative circular dichroism. This is on the scales of millimeters. In just a second, I'm going to show you a higher resolution set of data, not with X-rays, but with optics. So for the last, again, 2 years or so, this paper is yet to be submitted because we've been going back and forth, back and forth. We said, hey, can we probe all of this, not with resonant X-rays, which is a very sophisticated synchrotron-based technique, but can I do this with optical techniques? And yes, you can. Marcus Rashka, one of our colleagues at Colorado, he's been helping us with these measurements, which is basically doing second harmonic generation experiments with circularly polarized light. This is the left circular, and this is the right circular image of the same area. And the difference between them clearly shows that you have circular dichroism. Regions which are in red are strongly positive circular dichroism. Regions which are in blue are in negative dichroism. Even more interesting, and this is really kind of the big statement, is even more interesting is you can now put metal electrodes. The black stripes here are metal electrodes. You can apply an electric field. You can switch the sense of handedness. You can switch not the sense of handedness, you can switch the circular dichroism. And because we interpret the circular dichroism here as coming directly from the chirality or the handedness, we believe that you can now manipulate the chirality with an electric field. Imagine that you took, and this is just imagination, it's not real. Imagine you took D-glucose, applied electric fields, converted into L-glucose. That's what we're trying to do with these systems, switch the handedness of the system and start to think of handedness perhaps as an order parameter. Okay, we can do very fast manipulation with state-of-the-art synchrotrons. These are all the ultra-fast capabilities, and this work was done in Japan. You can start to take these vortices and you can start to excite them. And it turns out that they don't go by themselves, they go up and down as a group. And that is called a vortexon. It's kind of a collective excitation of these vortexons with the frequency of about 200, 300 gigahertz. So you can do terahertz optical manipulation for all these things. So you can look at these modes. They will go up and down like a scissor, go back and forth. So these are collective modes of oscillations of the vortices. And if you look at what happens, if you come in and shake this is phase field calculations, time resolved. And that's cooling down from high temperature. This is the lead titanate layer. In about 10 picoseconds, you could start to see the vortices nucleate at the interface between the strontium titanate and the lead titanate. And they will start to move right to the center of the vortex, of the layer, in about 40 picoseconds. Okay. And this is the kind of the summary of that calculation. If you look at the lead titanate layer, it reaches the equilibrium energy very quickly. Maybe tens of picoseconds, maybe 100 picoseconds. The strontium titanate, on the other hand, takes almost 40 picoseconds time, which is approximately the velocity of sound. So the question is, how does this happen? Is this because phonons are kind of nucleated at the interface? What is the microscopic mechanism? We are still scratching our head, so this work is still not published. Okay. A quick summary of this part, and then I'll quickly summarize the skyrmions, and then we'll be done. So I talked about the vortex lattice has pairs of dislocations, kind of looking like a clusterless thallus, and we need to do more work on that. And we can see all these defect structures in them, antiphase boundaries. What happens to chirality across this boundary? We need very high resolution techniques. I showed you data of probing chirality with resonant X-rays and with the second harmonic. And we also showed you that, in principle, you can manipulate the chirality with an electric field. Now, our theory colleagues for a long time have been telling us, guys, if you just change your lattice mismatch, you will go from a vortex to what you call a skyrmion. And we said, yeah. For about a year and a half, we went back and forth. And the microscopy fellow said, oh, I see nothing at all. Then I said, no, we're going to go do the experiment. And indeed, when you go from dysprosium scandate, which is a tensile substrate, to strontium titanate, which is essentially dead-on lattice match, we start to see skyrmions. And indeed, the phase field guys had predicted that this is strontium titanate. You could see these bubble-like features. And on dysprosium scandate, you see these vortex-like features. And it took us a while to get to this. You had to really be carefully controlled. This fellow, Sujit Das, I have to put in a word for him. This guy is an amazing MBE guy, oxide MBE guy. He's a lab rat. He likes to do growth all the time. He cannot find a job in India. He desperately wants to go back to Kolkata because his parents are old and stuff. They're sick. But he's been struggling to find a job. One of you guys can find him a job. I think he would be very happy. He and his collaborators, we showed that indeed you can form these skyrmion-like structures. I'll show you one in a little bit higher mag. That is kind of a local area picture of the skyrmions. Each skyrmion is about 6 nanometers in diameter. That's about the size of this picture here. It has short-range order, but it doesn't have long-range order. This is one of the questions that we're trying to understand. Why does it not get into a long-range order structure? Is it the same kind of physics as ordering in a 2D lattice? But it turns out that even with the existing degree of order, we could do a lot of things with this. You can characterize like the magnetic skyrmions. You can name the skyrmion number, which is this integral over the surface of the skyrmion. And this term is called the Pontergin density. Okay, and it's a function of this vorticity of the skyrmion rotating this way or this way. So again, ab initio theory said exactly the same, that if you look at the top of these skyrmions, it looks like a porcupine coming out like this. Those are the nail part of this skyrmion. If you look at the bottom, it is going underneath it and it's coming up. But the most fascinating thing that the theory guys were saying was, guys, we also see an in-plane component. It looks very much like the belt that you wear. That's the one, in this case, is going counterclockwise. That's a block component of the polarization. And it turns out lead titanate has this behavior. From ab initio, people have shown that it does have these kinds of behavior. And it turns out experimentally we can see it. Let me just show you a quick video. This is kind of a nice visualization of these skyrmions. Perhaps I'll show you just the video of this. One of the students in Long Chen's group at Penn State, he seems to be a really good artist. And so let me see if I can play this video. So you can go right into the skyrmion, and you will see that it has this nail component, but it also has the block component, and it's going to show up right at the end of this. There's a cutout where he made, where you can see the block component right here. Okay. So this has both components. It has both the block and the nail component. So formally, these are called Hopfions. Then we said, let's go back and see if we can image the block component. We went back to David Mueller, and his postdoc again did a fantastic job. And we were able to image both in cross-section and in planar section what the structure of this skyrmion was. And this is the actual image of a planar section. It's called 4D stem because it's momentum resolved stem. This is absolutely the state of the art. It didn't exist when I was doing my PhD on microscopy. It is just so fascinating what these guys can do. The calculated images from first principles actually agree pretty well. This is a little bit more sheared, but overall it agrees very well. Subsequently, we have gone and imaged hundreds of these kinds of skyrmions. They all have the same sense of rotation. This rotation that you see with these arrows is all in the same direction, which is very fascinating, which says that the entire ensemble of skyrmions has the same handedness, which is very fascinating. We don't understand why they all have the same handedness. Why did it not pick up a left-handed versus a right-handed? That's something that we are still trying to figure out. Sujit, again, did a fantastic job of growing these. They must have grown about 200 samples to make sure that they absolutely got these skyrmion structures. Then David Miller's postdoc has been working on this. One of the questions that we were trying to ask, as I mentioned earlier, why do these things not order? And it turns out that if you do very small tweaking of the strain state, and in this case, we lift off an entire membrane of this skyrmion, we can now do that over hundreds of microns. So we can have large areas of skyrmions where you can start to look at, collective effects. You can look at the phase transitions in the skyrmion lattice. At very low temperature, if you look at these images, that's the actual image. This is the processed image. It starts to form what we call serpentine or long needle-like domains. As you go from 223 to room temperature, it starts to break up, kind of like a Rayleigh-Taylor instability. It starts to break up, and if you look at the phase field, that is exactly what it's predicting. There is just a very small change in the state of strain in the system. And then if you go to slightly higher temperatures, about 80 degrees C or maybe 100 degrees C, you start to see on a local basis, these skyrmions begin to order. If you look at this, this is the vector map again for the block component. You could see that very clearly it is forming a lattice of skyrmions, albeit at a very, very small scale. We don't know how to make it over the entire sample yet, and we're still working on that. You can see that these guys are rotating counterclockwise, 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 counterclockwise. This is rotating clockwise. Even more interesting, right at the center, you could see the formation of an anti-vortex in the system. So it seems to be behaving, albeit at a very local scale, very similar to some of the magnetic results people have published already. So there is a parallel universe of polar skyrmions which have the same kinds of attributes as the magnetic skyrmions. They don't come for the same reason, but they have similar attributes. Now, it turns out that if you do the resonant soft X-ray circular dichroism measurements, I'm just going to quickly show you this data. Indeed, we see very strong circular dichroism for the skyrmions as well. And that's seen here in this picture. It is very antisymmetric. So it's telling you that these skyrmions are also chiral. Okay. So that, to us, this has been the big learning that you can take two materials, lead titanate, strontium titanate. Of course, lead titanate breaks inversion symmetry. Strontium titanate is cubic. You put them together, you create these kinds of textures, and the material is chiral. And you can manipulate that chirality with electric fields. Very fascinating. Last piece of that data, and then I will finish up, is this was the recent paper that Sujit published a few months ago. You can now take this superlattice. This is an N-layer superlattice with the skyrmions built in. And if you measure the macroscopic dielectric permittivity, it is huge. It's about 800. If you look at lead titanate, it should be about 70. Strontium titanate, 50 nanometers, should have been about 150. And if you put them in series, the net dielectric constant should be near the dotted line for just simple dielectrics in series calculation. Instead, the dielectric constant is huge. If you apply an electric field to it, that dielectric constant can change by about 75%, which is just dramatic. As a function of the superlattice periodicity, this is a tri-layer, 3 repeats, 5 repeats, and 8 repeats. The magnitude of the dielectric response becomes larger and larger. And actually, second principles, phase field, all of them are predicting essentially the same kind of a trend. Okay? Now the question is, why does this happen? If you look at this picture, this is calculations. This is telling you what happens with the electric field. As I apply an electric field, a skyrmion ensemble, which you see here in this picture, it starts to shrink. Shrink, 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 shrink. And at one point, the skyrmions completely go away. And at that point, the material has become a normal ferroelectric. And therefore, if you look at this picture, that dielectric constant is approaching that of the bulk material. It is not a topological material anymore. It doesn't have any of the topology of the skyrmions that you saw. So you can now go back to, again, first principles calculations. This is Javier Junquera. Umesh, we used to talk to Umesh a lot in the early days. Javier Junquera does all the theory for us. What they showed was very interesting and intuitively obvious. The susceptibility of the skyrmion is very large. You can look at these brown rings right around the periphery. And you can understand that because that's like the domain wall, the material is very deformable. Okay? And if you then plot the inverse of the permittivity, which is plotted here, you can see that that inverse is actually negative. The 0 is here, and the red is positive, blue is negative. that permittivity is actually negative. Very much like what you expect for the vortex case as well, which was the core of the vortex. Now this is the periphery of the skyrmion that's got negative permittivity. And this is phase field calculation showing you that blue region is where you have negative permittivity. You can then use a classical electrical engineering model of capacitors in series and in parallel, and you can model it to say, what do I need to do to get effective permittivity of 800? The only way that you can do that is by having negative permittivity. This E3 has to be negative, which means that's the permittivity of the periphery of the skyrmion. So again, like in the case of the vortex, these skyrmions harbor negative permittivity within them, which means that in the ensemble, you have regions of negative permittivity, although the net permittivity of the material, as we just measured, is still positive. Okay, and this permittivity, by the way, is not just at low frequencies. Typically in our labs, we measure at a megahertz. This we can go to 10 gigahertz, and right now we have gone all the way up to 100 gigahertz. You can start to see that it's decaying, but it's still significantly enhanced over strontium titanate, which is the higher dielectric constant material. So these huge enhancements in the dielectric permittivity are enhanced all the way up to 100 gigahertz. And so if you're practically minded, you can start to think of these as tunable dielectrics. You can start to put a lot of other things into the system. For example, we are looking at putting in single spins into this and see how those spins couple. It turns out the spin orbit coupling is very important. And so you can start to manipulate that. So I'm kind of getting to the end of my presentation. I wanted to just point out the skyrmions and the vortices, very different. These skyrmions look like, cylinders in some sense. Vortices look like cubes. They're in plane, and you can see they're all pretty well aligned. This is in a superlattice. This is in a trilayer. If you compare magnetic versus polar skyrmions, the free energy density, of course, has the exchange term. The Dzyaloshinskii-Morier term is very important. In the case of the polar skyrmion, there is no Dzyaloshinskii-Morier. It is these two terms, the electric and the elastic terms. And so there are some things which are very similar. Anisotropy, for example, is very strong in skyrmions. It's typically not strong in magnets. So it is this interplay between various energy scales that are really important. So I will stop with this slide. We think that there is a whole universe to be tapped into using epitaxy. You can start to replace lead titanate with other materials, etc. You can start to look at, all kinds of new phenomena, ordered polarons, magnons, excitons, chirality we already talked about, magnetoelectric coupling. So there's a lot to be done. If you're a fresh graduate student, this is a great field. So Didi and Vivek, thank you so much. Very happy to take questions.
Thanks a lot, Ramesh, for a fantastic talk as usual. Very, very inspiring and absolutely fascinating. Fantastic.
Thank you. Yeah.
So I hope there is some moderator who would be helping me with if there are questions in the chat box. So far, I haven't seen any question in the chat box. Alternately, participants can raise their hand, and I'll try to take note of that and direct to the. Okay, there's Shubhankar Vedanta from NICE. He has raised his hand. So Shubhankar, you can unmute yourself and ask the question. I request others to remain mute.
Yeah, good morning. Excellent presentation. Thank you so much for this nice overview.
Thank you, Shubhankar.
In skyrmion case, you have anti-skyrmions, merons, then skyrmion. All these families have come up very well. So in this polar skyrmion, do you have also such families, or you anticipate or expect that will also happen?
Absolutely, Shubhankar. You hit a fantastic question. Literally, this is something we're working on. Again, Sujit is trying to finish this up before he goes for another postdoc in Europe. We know that you can form merons and anti-skyrmions and stuff. There are other people, for example, some groups in China, which have predicted these things. So we think you're going to see a lot of new animals in the zoo.
Okay, really looking forward to that. Thank you so much.
Yeah.
Okay. Shubhankar, if you can lower your hand, is there any other person I have a couple of questions, but I'll keep it at the end. Yeah, Ajay Singh, I see your hand going up and down.
Yeah.
Okay, please go ahead
Yeah,
and ask a question.
Professor Murthy, very exciting talk.
But just Ramesh is okay.
Actually,
No professor.
Yeah. And
Yes, Ramesh is okay. Yeah.
Actually, I wanted to ask a question related to the phonon localization, where you have mentioned that when decoupled, the phonon degrees of freedom get seized up and they show a localization. So my question is whether this localization is dimension dependent, whether it will happen in say bulk and 2D or a low dimensional system, because then you have anisotropy and the optical and you can say the electromagnetic contribution to that will be missing somewhere.
Yeah. This is a fantastic question. This is an awesome question. With Arun, we have had so many arguments about this. We think that you need these kinds of dimensional confinement. Actually, if you look at the original paper by Professor Mahan, Simpkins and Mahan, they wrote a paper in PRL, I'm going to say 1991 or sometime like that, where they actually said that, hey, if you had superlattices of silicon and germanium, you can start to create this. You definitely need to have some dimension of the material which is close to the dominant phonon. Of course, these are bosons, so you can have all kinds of wavelengths. But at room temperature, any temperature, you will have one dominant wavelength. And therefore, you need to be in that length scale for you to start to see the coherent behavior. So I'm very convinced. I don't think we know the answers yet. I'm very convinced that you need to have certain dimensions satisfied for you to start to see signatures of localization. And the easiest way to look for localization is to see what happens to thermal conductivity.
Yeah, because there will be backward scattering. There will be backward scattering.
Right. Yeah, you could have overlap scattering.
You're right. Now, a small adjacent question to this is the standard band gap which form in Crony-Penny model, usual solid state physics, because students are here. If we have localization of the phonon, say, then there will be a formation of the gap because of the decoupling of electronic degrees of freedom from lattice will generate scattering also.
Yes.
And during that interface, this gap will be actually depend on the coupling of electron and phonon degrees of freedom. So
So here's one thing to keep in mind. In this case, there are no electrons. These are insulators, right? But having said that, I mean, you could have dipoles. The dipoles do couple very strongly to the lattice, right? But I totally agree with you. There should be a gap that opens up in the system. To the best of my knowledge, nobody has measured the gap which opens up because of the formation of either the skyrmions or a phonon localization. Nobody has measured it, including ourselves. No.
There are a couple of more questions, so we have to move on now. Next question by Shubhankar.
Yeah, thank you, Didi, and thank you, Professor Ramesh. Yeah. Can you hear me?
Yeah. But no professor. Okay, just Ramesh.
Yeah, Ramesh, thank you so much. This is a fantastic talk. I have a very quick, but maybe a stupid question. For magnetic skyrmion, if you have a conducting magnetic skyrmion, one of the thing is the Bailey phase physics coming through the topological Hall effect.
Mm-hmm.
Some kind of possible analogy for this.
Yeah, exactly. Hey, it's a great question. It's not a stupid question. We have been arguing the heck out of each other here. What is the analogy to the Berry phase formalism and for the Hall effect in the magnetic skyrmions? It may be the chirality. We're not sure, but we don't know the formal parallel universe in a dielectric system as in the case of a magnetic system. And none of us have, even our theory colleagues, we are all kind of debating it, but we don't know the exact analog of the topological Hall effect in a magnetic skyrmion.
Okay. Devkanta Samal, next question.
Hello.
Yeah.
I have a very general question. like electronic interaction that gives rise to various phases, we know. In the case of this fermionic, those kind of interaction, do you have a kind of phase, various phases that we expect that various phases can emerge? Like electronic interaction can give rise to various phases. So what do you understand about this?
Yeah, by the way, this is again a fantastic question. If you recall, in the beginning, I showed you, the vortex lattice, right? And the vortex lattice was a 2D object. Think of a bunch of cigarettes. Nobody smokes cigarettes anymore, but think of a bunch of cigarettes that you're laying them down. And so you could have phase transitions in those, right? Of course, it may not be completely go into one state because 2D effects may completely show up, but you could go from completely ordered. Let's see if I can quickly go back to this picture that I showed you. Yeah, this is in some sense an example of that, Shubhankar, in the sense there are phase transitions going from a disordered state to something which is ordered state. Yes, on a very local basis, but still there are transitions that are happening where it goes from having no long-range order to this guy, that I or F, where you can actually see something like a diffraction pattern. And you can see that in the top there. There's a clear indication of a diffraction pattern telling you that there is long-range order. And we have actually done measured the radial distribution function for I and H. They look very different, significantly different. So yes, you can do that. And I think you will start to see a whole series of phases where the unit is not the atom anymore, but it's a skyrmion. Does that make sense, Shubhankar?
Yeah, thank you.
I think we have run out of time. Otherwise, we would have loved to take more questions, including several of mine, but we have to skip all of them.
You can email me.
You can always reach out. Yes, so you can always reach out. I know Ramesh would be happy to respond. So if you have questions, please reach out to Ramesh, and I myself will do that. Yeah. Let's thank Ramesh once again.
Thank you very much,
fantastic
guys.
talk. It's been a wonderful experience. Wonderful.
Thank you, Vivek. Thank you, Didi. Yeah.
I can see Masashi is ready out there, so let me have. I'm very, very happy. Hi, Masashi. Hi. Wonderful to see you. We should meet soon in person. Let's hope we'll be victorious against this.
Kawasaki Sensei.
Hi, Ramesh.
Good to see you, my friend. Good to see you.
Hi, Shubhankar.
So it's really my pleasure to introduce the next speaker, Professor Masashi Kawasaki. He is extremely well known world over for topological electronics, oxide thin films and interfaces, and topological materials. In fact, one of our prime organizers of this conference, Professor Shubhankar, was trained in Professor Kawasaki's lab. And Professor Kawasaki's affiliations, he's a professor at Department of Applied Physics, School of Engineering, the University of Tokyo. But he's also deputy director of this very big, very important Riken Center for Emergent Matter Science, and he's group director of the Strong Correlation Interface Research Group at the same center, Riken Center. So Masashi, it's a 45 minutes, take about 40 minutes to give the talk, at least leave 5 minutes. I'm sure there'll be a lot of scope for discussion. Yeah, so sure. when you see that my video is coming on, that means it's 40 minutes over. Okay. I don't want to interrupt you otherwise. Yeah. Please go ahead.
Yeah, thank you very much. Thank you, Didi. First of all, I would like to thank the Shubhankar and all the organizers for this invitation. I'm very glad to see all those Didi, Ramesh, and Shubhankar and other people. Okay, let me talk on the zinc oxide, which is thought to be a boring wide bandgap semiconductor, but this is not true. So we can enjoy very nice correlation physics. Okay. So those are the my colleagues working together. Key player is Joseph Farson, and we are working on zinc oxide for like 25 years since my very young age. And the mobility of electrons in two-dimensional electron gas in zinc oxide exceeds now 1 million. And we are seeing quite different physics than compared with conventional semiconductor physics. And today I want to talk two things. One is this even denominator fractional quantum Hall states, which is thought to be a topological superconductor. And the people are talking about this may be an enabler of topological quantum computation. And the other is a possible superconductivity. We don't know yet whether this is superconductivity or not, but the phase diagram looks quite similar to that of ITC cuplet superconductors. And I want to discuss all these two topics. Okay. I don't know. Just a moment. Yeah. The oxide is known to be a very useful material, but usually useful material tend to be very dirty. And the people add some ingredient to make very useful device parameters, so such as capacitor or inductors and such. If you think about the pure material, you may think about something like silicon. And the silicon crystal is known to be such pure, like 99.99. So 13 or 11 digit, you have a continuous 9 in the purity. But as a matter of fact, even silicon has a lot of impurity, which is oxygen. So you cannot avoid oxygen impurity in silicon. And usually in Czechoslovakia grown silicon tend to have oxygen impurity of something like 1 to 10 ppm. So this is a conventional impurity level in silicon. And if you say pure material, people may say gallium arsenide. The cutting edge cleanest, MBE grown gallium arsenide can be very clean. And this is one of the top-notch MBE, which produces very high purity, gallium arsenide. And this vacuum chamber have a 10 to the minus 12 residual gas. Those residual gas is CO2 or H2O, bunch of the oxygen source. And in order to avoid oxygen contamination, all the loading chamber is capped with some glove box, and inside of the glove box is filled with argon, but still have 30 ppm oxygen. So you never be able to avoid oxygen in the gallium arsenide. So the very pure gallium arsenide thin film tend to have, roughly speaking, sub ppm, but never be cleaner. So if you don't like oxygen as an impurity, the best way to take an oxide, so you don't have to worry about oxygen as an impurity. So oxide likes oxygen. So on the globe, you'll never be able to avoid oxygen as an impurity. Okay, so zinc oxide is such a white powder, and people use it in sunscreen, and many, zinc oxide is used in the automobile tire to make this rubber harder. And I have been working on zinc oxide for a quarter century, and in some 90s, we realized that nice zinc oxide thin film can generate exciton related laser emission at ultraviolet light and even at room temperature. And this triggers a lot of work worldwide. And it took us 8 years or so to make PN junction light emitting diode. And we are the first who made all oxide, zinc oxide PN junction, which emits UV light. And then we work together with the Japanese company RAW to make this zinc oxide LED in the market. But we failed it, but instead we made a nice, another route to enjoy some quantum Hall physics in zinc oxide. And in 2007, the first quantum Hall effect in oxide is realized in zinc oxide. And since then, about 15 years has passed, and our understanding of very nice correlation physics in this very simple oxide semiconductor. Okay, let's look at zinc oxide. Compared with gallium arsenide or silicon, which is a diamond or zinc blende structure, this zinc oxide takes a wood side structure. So this octahedron has a asymmetry, unlike wood side, unlike a zinc blende. So this has not only broken inversion symmetry, but also spontaneous polarization. Along C-axis of wood side, you have electronic polarization. And if you take this thin film or heterostructure or substrate, you have to have electronic polarization inside of the crystal wafer. And then if you take this spontaneous polarization, the electric field inside of the substrate must be something like 5 megavolt per centimeter. But this does not this cannot be real in real world. And always we have surface contamination or electric double layer. So inside with crystal, the band structure tend to be flat, and at the surface of the backside and front side, you have some double layer or some electric field. And if you put two slightly different material, one is pure zinc oxide, the other is slightly magnesium doped zinc oxide, because of the different ionic radius of the magnesium and zinc, this electric spontaneous polarization is also slightly different. On the surface, you can make double layer to compensate this surface charge. But at the interface, there is no garbage. So you have to accumulate electron in order to match or compensate these different values of surface electric charge. That is the origin of accumulating electron at the hetero interface in the narrower band gap side, which is zinc oxide. And if you plot the electric polarization and the magnesium content, you have very linear relationship. And as a matter of fact, the electron density accumulated on the interface also has linear relation. So just impurity concentration or magnesium content can just predominantly determine electron concentration. And these are the cartoon of the two-dimensional electron gas. Our zinc oxide looks like that, different band gap, and having two-dimensional electron gas in the zinc oxide side of the interface. This is a famous, modulation doped interface of gallium arsenide. And this is very first stage of the quantum Hall effect. People observe two-dimensional electron gas in silicon, and also the graphene is another playground for quantum Hall physics of two-dimensional electron gas. Okay, this is our history. This black one is the long history of the gallium arsenide. People start to observe enhancement of the mobility or transport scattering time. This is related with the mobility in this equation. And it took them 20 years to push up the mobility to the level where the quantum transport scattering time is about a nanosecond. This is our 8 years of the progress. The first quantum Hall effect is developed in pulse laser deposition grown zinc oxide, and we switch to MBE, and we tune up all these MBE to get higher mobility. And the zinc oxide has rival to the gallium arsenide in terms of scattering time. Okay, so if you plot the mobility as a function of charge carrier density, or if you change magnesium content, you can tune this electron concentration. Then the mobility tends to look like that. This side is determined predominantly by the interface roughness effect. If you put more electron, this electric field at the interface becomes sharp or large, then wave function is more pushed to the wider bandgap material of magnesium zinc oxide, and you have more magnesium. That's why this electron have a lot of scattering. But this side is coming from this impurity scattering. So if the sample gets purer and purer, you can push up this blue broken line to the left upper side. And the key is to make, a very clean material. And the one with breakthrough for us is to take the ozone or oxidizing zinc or magnesium in the MBE chamber. Then you can avoid all the impurity. So the mobility goes to close to 1 million at low temperature. And finally, if I tune up all the details of the heating system in our MBE, we can finally achieve very high mobility exceeding 1 million. As you can see, this is our 8 years progress, and we can readily, reproducibly, we can make a very high mobility zinc oxide. And this is very clean semiconductor. Let me show you how clean it is compared with conventional semiconductors. Okay, so let me talk a little bit on the tutorial view of the quantum Hall effect. If you have an electron confined in 2 dimensions and apply magnetic field in perpendicular direction to the surface, you have a cyclotron motion. Left-hand side is a dirty semiconductor, or in this case, you have lots of scattering, but if you apply magnetic field, on average, electron feels some Lorentz force, and on average, electron shifts to the orthogonal direction compared with this current flow direction. And this is a Hall effect, which is linear to the magnetic field and very small magnetoresistance. Whereas if your two-dimensional electron is sitting in a very clean surface, this electron magnetic field makes a circular, cyclotron motion. And the low magnetic field, this diameter of cyclotron motion is big. And if you make a higher magnetic field, this cyclotron motion becomes, the radius becomes small and small. And the nu equal 1 corresponds to 1 wave in a 1 orbit. Nu equal 3 corresponds to 3 waves along this circular motion. And if you plot the Hall resistance as a function of magnetic field, instead of having such a straight line, you have staircase. And each steps, you have some certain number of the quantum resistance, and this can be used for the standard for resistance for years. And now people tend to use this quantum Hall effect as a standard for weight or kilogram. Okay, so in order to have this situation, first thing is this omega c tau must be greater than 1, meaning you should not have any scattering until electron complete circular motion. And the second requirement is h nu omega c must be greater than kT, meaning the energy separation between these quantized level has to be greater than thermal agitation. So this is the view. So if you don't have magnetic field, this in the conventional degenerated semiconductor, then stable state is say nearly constant, and you have many levels. But once you apply magnetic field, all these states degenerate in the quantized states. Then if you make a magnetic field greater and greater, this energy separation between the random level becomes bigger and bigger. And the number of levels below the Fermi energy is your filling factor. This is filling factor 1, and 2, and 3. And this is because of this topological view, this is known as a topological effect of electron wave function, and a very old topological effect. So a more easy view is something like that. If you have 3 quantized level field, and the fourth one is empty, your Fermi energy is in between this gap. So body, bulk is insulating, whereas at the edge, this quantized level cross this Fermi energy. That's why at the edge of the sample, you have so-called skipping mode, and this is metallic one-dimensional current path, and the rest is totally insulating. This is similar to this outbound in Germany, and the electron here goes this way, the other way goes this way. So let me tell you how clean it is. So this is a low magnetic field, Dohas oscillation. Low magnetic field oscillation means in a low B field, your cyclotron motion, the radius is very large. So electron has to pass through very long distance before completing one circular motion. And having such a low field, and you still have quantum interference, means electron does not have any scattering when complete very big radius and circular motion. And by analyzing these things very accurately, you can deduce 2 things. One is the quantum scattering time, and the other is the effective electron mass. And quantum scattering time is more sensitive to any defect. Transport scattering time is just same as mobility. You just divide by electron charge and multiply effective mass. This is nothing but mobility. But here, quantum scattering time is more shorter, meaning forward scattering also matters. So in order to make quantum oscillation at low field, this you have to complete the electron cyclotron motion within this quantum scattering time. So this is very difficult. And if you compare this quantum scattering time with gallium arsenide, this blue is gallium arsenide best quality heterostructures, and this red is a zinc oxide. As you can see, quantum scattering time is similar. So the oxide semiconductor can be as clean as best gallium arsenide, and the mean free path is like 10 micron, and mobility exceeds 1 million. So having that kind of sample, you can now enjoy very interesting correlation physics. So the reason why we have such a very high mobility is that one is that we don't have any doping. In case of gallium arsenide, people have to dope silicon in a remote position from the interface, but still this ionized impurity of silicon gives a disorder for the two-dimensional electron gas. And the second is, you don't have to worry about this impurity of oxygen. Oxygen is a component element, so this is no longer impurity. So I don't know how to close these things. Just a moment. Yeah. Okay. So if you think about electron correlation, one of the very famous last decades, people are enjoying electron correlation effect in 3D elements oxides like manganite. And in case of manganite, electron sits on each atomic lattice, meaning electron distance is 0.4 angstrom, very short. That's why Coulomb interaction is very large. This Coulomb energy is about 1 electron. This is a Coulomb gap, charge gap in correlated electron oxides. What about in zinc oxide? As I told you, zinc oxide electron distance could be something like 10 nanometer or 100 nanometer. So I'm talking about charge density of 10 to the 10, very, very diluted electron system. Here, electron distance is only 100 nanometer, right? So Coulomb energy is something like 10 microelectron volt. In this case, 1 electron volt and 4 angstrom. In our correlation effect, our correlation energy is 10 microelectron volt, and electron distance is 100 nanometer. So in order to extract intrinsic physics from such a clean system, this perturbation or disorder, energy scale, landscape, flatness of the energy landscape must be less than 10 microelectron volt, meaning you have to have very clean material. Otherwise, every disorder in the potential landscape will kill you. Everything get into the Anderson localization. So if you have such things, we have to take into account 2 energy scales. One is kinetic energy or Fermi energy, and the other is Coulomb energy, or this is a electron repulsive force. So kinetic energy scale is that electron, you are pushing electron to move, and Coulomb energy is energy so that you are trying to stop electron motion. And this ratio is so-called Wigner-Zeitz parameter, RS. RS is just a ratio of these energy scale, and this energy scale is ranging from 1 to 10 in conventional gallium arsenide 2-dimensional electron gas, and here the other side is zinc oxide case. As you can see, one is that electron is heavy in zinc oxide, and the other is the direct constant is small compared to the conventional semiconductor. That's why this correlation constant is much bigger than gallium arsenide. And in our cutting edge sample, this correlation parameter or Wigner-Zeitz parameter goes beyond 30, and we start to see crystallization of electron at 0 field. This is very rare in any materials. Okay, and the other thing, a very important parameter is spin susceptibility. In vacuum, it's 2, right? G value is 2. And in gallium arsenide, G value is very small, like 0.4, but in case of zinc oxide in bulk, G is 4, 2 times greater than in vacuum. And if you look at this, all these quantized level, and if you apply magnetization, then a magnetic field upspin band and the downspin band split. But in case of zinc oxide, this is very small. Gallium arsenide is very small, but in case of zinc oxide, Zeeman energy is compared to cyclotron energy. So you have a lot of band crossing, and this band crossing gives a very important new physics. And in a best quality sample, very diluted sample, like a 10 to the minus 10, 10 to 10 charge density, this G value tend to be as large as 15. So this is a conventional, zinc oxide very diluted system up to 2015. Nowadays, we can make very clean sample with pushing down the charge carrier density in the order of 10 to the 10. So this is a so-called fraction quantum Hall effect. As I told you, this magnetic, as you apply magnetic field, you see zero resistance and the plateau in Hall resistance at each integer filling. And between these integer states, you have another quantum Hall effect, which is fraction quantum Hall effect. And this is thought to be an integer quantum Hall effect of these two, composite fermion. As this movie is very strange, but it should rotate on the circle. But 2 electron is attached on a single electron. And this looks like 1/3 of the charge for single particle. And that's why 1/3 is a very fundamental fraction quantum Hall states. And this is a cartoon, this is data is for gallium arsenide. And we are seeing very similar things in zinc oxide, or yet we see very new quantum Hall states. And this is a case of gallium arsenide. By applying magnetic field, you are reducing filling factor. You have more degenerated states. And you see very different type of these electron states. And we are seeing very different things in zinc oxide. So this is the zinc oxide. This is 1, 2, 3, 4. This is an integer quantum Hall effect. And in between, you have numbers of fraction quantum Hall effect. By the fundamental physical law, this fractional quantum Hall effect, the denominator must be odd because of the Pauli principle, Pauli exclusion rule. So this even denominator states must be compressible or metal, not insulator or not quantum Hall state. But in some states, you see this even denominator states gets quantized. And this can be, if you apply, if you tilt the sample in the magnetic field, you start to see this 3 halves, even denominator states also quantized. And this is thought to be a superconducting state, P-wave superconducting state. So having 2 composite fermion get paired, and that's why even denominator state is allo. So this is like a superconducting state. And in case of gallium arsenide, in case of gallium arsenide, like 30 years ago, people discovered 5 halves. And people understand this 5 halves is such state. This half-filled state is on the n equal 1 excited random level. And in case of zinc oxide, because of Zeeman splitting is huge, this downspin state of n equal 0 is coming higher energy than the upspin band of the excited random level. And because of this, crossover, the nu equal 3 halves, you have, filling of the 3 halves, and this is half filled. And this gives you quantization, and this quantization is thought to be like a forming pair of composite fermi. 1 electron capture 2 flux quanta, and these composite fermion get paired like a Cooper pair in superconductor. And this kind of particle gives you even denominator states. And this state is very interesting in terms of the topological quantum computation. This is theoretically predicted to support or obey in non-abelian statistics. And this kind of particle, by exchanging these particles, you can make a braiding kind of thing. And the people are working very hard for making topological, qubit, or with using this even denominator states. And in not only gallium arsenide, but also zinc oxide is on this playground. And unlike gallium arsenide, zinc oxide has 3 halves, and very important things is this is tunable. Switching on and off can be easily tuned by changing the Zeeman energy. So this is a new thing which cannot be done in gallium arsenide. Okay, this is the first topic of my talk, and let me go to the second topic, which is possible superconductivity in even cleaner or better sample. My colleague, Joseph Farson, was a postdoc in Stuttgart and now assistant professor in Caltech. And he spent a lot of effort in making very low temperature dilution leafage in Stuttgart. And he could succeed in making 6 millikelvin dilution cryostat in laboratory, and he can make a lot of interesting experiments. Okay, this is one of the data. So if you pick up very clean sample, like 10 to the 10, and if you can make a gating from backside, you can tune like a 50 volt to minus 50 volt to 30 volt. You can tune charge carrier density from less than 1 to the 10 to the 10 to the 2 times 10 to the 10. This kind of gating could be possible. And by changing this charge carrier density from 1 to 2, then you see this is wrong. Yeah. If you have more charge carriers, the system becomes metallic. And if you have less electron density, system becomes insulating. And this kind of metal insulator transition occurs right at the critical charge carrier density of 1.6 times 10 to the 10, which corresponds to the Wigner-Zeiss parameter of 30. And at the insulating state, we see so-called Wigner crystallization. And here we have metal insulator transition. This is quite new. And if you scrutinize this phase diagram, you see even more interesting. Here, this is magnetic field. And this is a charge carrier density modulated by gating. And you plot a column code of your resistance. And if you cut this way horizontally, this is nothing but the magnetoresistance. And this blue one, blue one is low resistance or zero resistance at certain magnetic field. And if you change charge carrier density, this zero state have some gradient. This is nothing but the integer quantum Hall effect. You see, quantum limit is approached only applying 0.6 Tesla, very dilated system. And these are, conventional integer quantum Hall effect. This is nothing surprising. This is rather surprising. You have a totally insulating state below 1.6 times 10 to the 10. And usually dirty material, it can be insulating, but it is coming from Anderson localization. But in this case, potential landscape has a randomness less than say 10 microelectron volt, very clean. So electron arranged in a triangular lattice, and this makes intrinsic insulating state, not like a localization. Even more interesting things comes here. At relatively high charge carrier density, where you have metallic state, but if you change the magnetic field, here you have a very big positive magnetoresistance. And I'll tell you, this is the process for spin polarization. So outside of this green triangle, electron is completely spin polarized or ferromagnetic. And even more interesting things, you don't see this interesting thing in this color map, but here you have excess conductivity or possible superconductivity. So bunch of things, Wigner crystallization, possibly antiferromagnetic Wigner crystal, and spin polarization, ferromagnetic, and in between metal and insulator, you have some excess conductivity. Let me tell you what is going on. First, let me tell you on the spin polarization. At relatively high charge carrier density, system is metallic at low temperature. What happens if you apply magnetic field in plane? So meaning, if you apply out of plane magnetic field, you end up boring quantum Hall effect. The interesting thing is if you apply magnetic field in plane, there's no cyclotron energy, but Zeeman energy is there. So you can shift the energy level between the upspin band and the downspin band. So if you apply magnetic field, downspin band is pumped up. So at certain stage, the all electron is sitting on the upspin band, like here. This is an indication. This magnetic resistance. At zero field, you have low resistance. By applying in-plane magnetic field, at certain point, this positive magnetic resistance saturates and it gets flat. Meaning this point is a magnetic field where you need to accumulate all the electron in upspin band. So outside of this saturation point, your sample is ferromagnetic or totally spin polarized. And by analyzing Shubidikov-Doherty oscillation, you can deduce G value. And as I told you, this sample has G value of 15. This is quite huge. And your Zeeman physics gives a very interesting phenomenon. Okay, let me go into the another stage, possible superconductivity. This is, as I showed you, by changing charge carrier density, insulator to metal transition occurs, and at a critical charge carrier density of 1.6. That if we map out these resistance in a two-dimensional map, one is the electron charge carrier density, and the other is in-plane magnetic field. And you plot all the color code, your resistance in a color code. And this dotted line, V-shaped black line, is the resistance tend to be quantized resistance. So the blue or green region compared with this black line, this is less than quantum resistance, and this is thought to be a non-polarized ferromiliquid here. And this dotted line is almost similar to this magnetic field, saturation of the spin polarization. And outside of here, spin polarized ferromiliquid is there, and here you have Wigner crystal. And between this ferromiliquid and Wigner crystal, you have very strange things. But if you map out this resistance in this color code, you don't see. But if you convert this color code to the B saturation is a denominator and the low at the magnetic field, then normalize this resistance value at the 0.2 Tesla. Then you see this one, and you see some strange behavior here, slightly dark, blue region here. And if you take magnetic resistance, still you have a positive magnetic resistance, meaning that this is Wigner crystal. Wigner crystal means ferromagnetic field Wigner crystal. All the electron, sit on some certain site, very repulsive force, and electron spin direct in one direction. But here, people believe some Wigner crystal having anti-ferromagnetic crystal spin orientation. And then from anti-ferromagnetic Wigner insulator to the metal, you have some strange, reduction in resistivity. That this is a low T. At Wigner crystal, you have a very insulative behavior, and in the very metallic state, you have a boring metal. And if you take IV curve or dynamic resistance, you see metallic state number 3 is quite boring, just a metal two-dimensional electrons. And one is this Wigner crystal, as you see in IV characteristics, you need certain voltage to slip all the crystal. This is something like a slippage of the charge density wave. You need certain threshold voltage to drive electron, carrying charge. But in between, if you see this dynamic resistance, you have a dip in resistance nearly at zero current, meaning this is excess conductivity, very similar to the superconductivity. And it never goes to true zero resistance, but we see this and this excess conductivity can be easily killed by magnetic field. And this is a quantum Monte Carlo simulation. As I told you, the electron is sitting on the single electron pocket at gamma point. The band is quite parabolic. nothing special, very, very, simple electronic structure. So we can take jelly model and the known potential disorder. So this is a very nice toy. So for theorists, it's very easy to, model this electron system. And this is the result of quantum Monte Carlo simulation, and this is our experimental results. And the simulation indicates that we have anti-ferromagnetic Wigner crystal here, and the paramagnetic field liquid, and by applying a high field, you can get a spin polarized ferromagnetic or ferromagnetic state, and in between, you have some excess conductivity. And if you plot resistance as a function of temperature and charge carrier density, you have an anti-ferromagnetic insulator, you have some excess conductivity, and this is boring metallic state at high temperature. So if you plot these things in the very familiar phase diagram, vertical axis is temperature, horizontal axis is charge carrier density, less charge carrier density, you have anti-ferromagnetic insulator, and the more charge carrier density, you have metal, and in between boundary, you have excess conductivity. So this is very similar to that people have been observing for high TCQ plate. If you go back and forth, it's almost same, except for temperature is 1,000 times lower. So this is a very nice material system where you can extract some very interesting physics. Okay, let me summarize my talk. I talk on the progress of making high purity zinc oxide by using molecular beam epitaxy. And the second topic, I talk on this, possible P-wave superconducting state of composite fermion, which is realized as the even denominator quantum Hall state. And third topic is that in a very diluted, very clean system, we see very strange electron phase transition between the anti-ferromagnetic insulator, which is supposed to be an anti-ferromagnetic Wigner crystal. So Wigner crystal is the consequence of electron collision, which is similar to the anti-ferromagnetic, MOT insulator in manganese or Q-plate. But this is a low energy version in zinc oxide, and you see some excess conductivity when you collapse this anti-ferromagnetic insulating state, which looks like a superconducting state. Thank you for your attention.
Thank you, Masashi, for a fantastic, wonderful talk. As exciting as always your talks have been. And it's really amazing what you have done with zinc oxide over the last nearly 3 decades of efforts, which has been enormous. I mean, it's almost heroic, I would say. Anybody who has questions? Yes, I see Professor Priya Mahadevan from SN Bose Center, National Center. Please go ahead and ask your question.
Thank you, Professor Kawasaki, for a very nice talk. So I have a couple of questions. The first is that, okay, it's a rather general one. You showed that you looked at the transport data to infer that you had the Wigner crystallization. Are there any other experimental probes which directly can see these, the size, the Wigner crystallization? And the second is related to that. And what is the, spatial extent of the localization? Do you have an estimate? Because I mean, as I understand, you have puddles of, metallic puddles in this, which is the Wigner crystal.
Yeah, it's a very good question. Actually, referee asked the same thing. Okay, we don't have any direct proof of the Wigner crystallization. So, yeah, people have been arguing how we can visualize this crystal formation in real space, like using, a probe microscope, because this is, each dot corresponds to charge. So, and the distance between charge is 100 nanometer. So, if you have a very good microscope, could be done. But unfortunately, our electron is sitting 500 nanometer beneath the surface. We have zinc oxide, magnesium zinc oxide heterostructure. And the top magnesium zinc oxide has a thickness of, say, 500 nanometer. So from such a far away, you cannot really see this dot. We have been talking with many, experts of the probe microscope. Other things like, ultrasonic, things and other things experimentally done in gallium arsenide. But we never do such a complicated experiment in zinc oxide. So we don't have any direct proof. And second question would be, if you have a mixture between the Wigner crystal or metallic state or something, we don't have any special typical length scale. But we see, for instance, this paper, Marienko 2018, this paper argued the mixture of the Wigner crystal of electron and the decay of the composite fermion. So this Wigner crystallization occurs right at the fractional quantum Hall state, and there is a mixture between the crystal and the decay. And crystal is formed by single electron, and the decay is formed by composite fermion. But we don't know length scale of this phase separation. This is my answer.
Next question by Shubhankar. Shubhankar, you have to unmute yourself.
Unmute.
Okay. Shubhankar, you have a question. You have raised hand. You have to unmute yourself.
Yeah.
Okay.
Thank you, Kawasaki Sensei. How are you? Thank you, Kawasaki Sensei. First of all, I just want to clarify one thing, that you see this metal insulator or this kind of magnetic phase transition when you apply the magnetic field in plane, right?
Yeah.
Is it true? Okay. So if you apply a vector magnet, for example, you keep your in-plane magnetization, and if you apply out of plane and measure the Hall, do you see any signature of anomalous Hall or something? Because you have different type of magnetizations, right?
Okay. Actually, yeah. You have you point out very important things. Let me show you something. No, I can't. No. Okay, this is one of the example. So if you apply both vertical magnetic field and the in-plane magnetic field, experimentally what we are doing is we rotate sample in the magnetic field. So if sample is completely aligned vertically to the magnetic field, this is only vertical magnetic field. And if you rotate, you can divide this magnetic field in a sine and cosine component. And the cosine component is E-plane, and sine component cosine component is out of plane. And this is one of the example. This is a new filling factor, meaning magnetic field in a perpendicular direction. This gives you cyclotron energy gap, right? And this is a ratio between the Zeeman energy and cyclotron energy, meaning if you tilt more with keeping same perpendicular magnetic field, then you can add in-plane magnetic field. So with keeping cyclotron energy same, you can change linearly the Zeeman energy. So by that, if you look at this vertically, you see this quantum Hall states at same filling. And this is, by adding in-plane magnetic field, you are adding Zeeman energy. And that is a very interesting thing for this zinc oxide, because, let me see, as I told you, in case of gallium arsenide, cyclotron energy is big, but Zeeman energy is quite small. So you cannot enjoy Zeeman physics. But in case of zinc oxide, since cyclotron energy and Zeeman energy is comparable, by applying, tilt angle, if you change tilt angle, you see this level is crossing. And that's why we observe even denominator states. So this is one thing, right? And the other thing is we applied completely in-plane magnetic field in our in my second topic here. This one, right? We apply magnetic field totally in the plane, so you don't have any cyclotron motion. So that's what we are doing. By applying in-plane magnetic field, no cyclotron motion, but there is Zeeman energy. Then energy for the upspin electron and downspin electron can be changed. That's why at certain magnetic field, you don't have any cyclotron motion, but your electron is totally upspin above this field. Then you can analyze everything in a spin polarized or ferromagnetic state. That makes everything simpler. That's why we play with this in-plane field.
We'll move on. We'll move on because there are several questions. I would skip the queue and request Ananda Bhattacharya to ask his question because he's in a totally different time zone, I suspect. and it's a very inconvenient time zone for him.
No, it's just fine. Hi, Professor Kawasaki.
Good to see you
again.
Go ahead,
I had a question for you. So my question is, I'm really curious about this G factor, and you mentioned, how do you tune it? That was my 0th question. And actually, the other question that I have is regarding this nonlinear IV you see near the Wigner crystal phase. In that, that reminds me of BTK a little bit. The way you draw those things look, the curves look, blonde income flat white kind of curves. And I'm wondering, do you see do you see any anisotropy in your conductivity? Firstly, in your Wigner crystal, and do you see any stripe-like physics or anything like that in your in this so-called superconducting region?
Okay. First question, this G value. This region, it's a conventional coincidence method. You rotate sample in a magnetic field and measure this resistance spike to match with this band crossing. And this one is different. This one is coming from this one. So this is, we measure the saturation magnetic field, which is critical B. And if you divide B by the charge carrier density, this corresponds to susceptibility along with this equation. So this is a different way, but still we measure it. And second question is whether we see anisotropy for this, say this one. For that one, we don't see any anisotropy. And but in another case, we see like a stripe case in some cases. That is, I showed you to Svanka last time. But here, in one direction, resistance is very large, and the other direction, resistance is 0. And we suspect this kind of stripe case. So for such an insulating phase, or insulating stripe, we observe. And this is like a charge so charge in some state, charge is accumulated in order to get insulating quantum Hall state, and the other you have a compressed metallic state, and this makes some stripe. But for this excess conductivity, we don't see. Is this what you asked?
Yeah. Thanks. I think that tells me what I want to know. I should probably just pursue further on the email or something because I have a lot more questions. Yeah. So
I have a very small question, Professor Masachi.
May I know who's the speaker who's asking question?
This is Vinod Ashokan.
Okay. Yeah. Please go ahead.
I have a small I have a small question. It will take hardly 1 minute. Do you observe the Wigner crystallization in very high density where RS is less than 1?
No. Less than 1, no. But like a 5 or 10, if you apply high magnetic field, we can see. But at this point is we see Wigner crystallization at 0 field at Zeiss parameter of 30 or 35. This is new. If you have somehow kind of a dirty material and applying magnetic field, then it's very easy to observe Wigner crystallization. But in my case, today's presentation, we see Wigner crystallization at 0 field. This is the point. But Wigner Zeiss parameter of unity, I don't think you can observe Wigner crystallization. This is just a metal.
We'll take the last question.
Okay, thank you.
We'll take the last question from Ajay Singh.
Yeah, thank you, Professor. Mr. Singh, I wanted to ask the last slide-based question where you have shown to a superconductor transition, zinc oxide. It's just like a copy of high TC phase transition.
Yeah.
The origin of this magnetic to superconducting transition is more on exchange, because exchange energy is small. You have only demand term, which basically under magnetic field will lead. So what is the origin of this transition? It's more of electronic degree of freedom or magnetism?
I don't know. I don't know.
Nobody knows.
I don't know. And also, I don't want to say this is superconducting. So, we call superconductivity, but this is typical phased superconductivity. Resistance drops, but never goes to zero. But if you apply magnetic field, it jumps up. Something like that. So we never know even if this is superconductivity, we never know any mechanism.
Okay, I think with that, because we are already overshot the time session. So let's thank Professor Kawasaki for a wonderful talk. It's fantastic. Both the speakers, Professor Ramesh and Professor Kawasaki, for fantastic talks, getting this conference started with a very big bang. I'm sorry that I allowed the session to overrun a little bit, but there's a coffee break, and Shubhankar and other organizers are not supplying us with any coffee, as we know. So I think we can steal time when the talks are so fantastic and allow the audience to interact. So with that, this session comes to an end. Yes, exactly. That is when we meet, Masashi. So,
all right.
We'll close this session now, and we'll reconvene in another 17 minutes at 11:30. Is that right?
Yes. Thank you, Professor Sharma, for chairing this session. And again, I would like to thank the speakers as well. Next session will start at, let's say, as you said, in 17 minutes. I have put the link for next session in the chat box. And Professor Arghya Tarafdar will chair the session. There will be 3 talks. First one by Professor Pratap Ray Chaudhary from Tata Institute of Fundamental Research. Second one from Professor Zakir Hussain from IIT Kanpur, and third one from Professor Devkant Samal from Institute of Physics, Bhubaneswar. The links are also provided in the program file, which I have also given the link in the chat box. So you can please, we are going to meet in, let's say, another 16 minutes or so with using the next link for that. If you have any question regarding it, you can ask now. Or shall we keep this, Swang? Shall we keep this session live for next 15 minutes or something, so that?
I mean, you can leave it live if people want to interact, but I don't think. I mean, it's very convenient to have 108 people talking to each other. So it may not serve much purpose. We can give a clean break and then come back. I think I'm going to log out anyhow right now, and I'll come back for the next session.
Yeah,
okay?
There's another
Thank you very much.
Okay.
Oh, announcement is there? Go ahead.
Yeah, for your talk tomorrow at 9 a.m. we are going to have another plenary talk by Professor D.D. Sharma. So please join that as well. Okay.
Vivek, you may close the session.
Yeah, okay, fine. I'll close. So link is anyway there, so anyone can copy, and this link is provided at the program file as well. Okay, I'll close the session.
Yeah.